is yours.
Thank you very much. So, final talk, almost there. Hang on. So, I guess my brief then was to give a kind of tutorial type of talk on ABC, okay? Approximate Bayesian computation. And I'll explain why I've got the approximate Bayesian computation in parentheses in a minute, okay? So just out of interest though, before we get started, who here knows about ABC already? Okay, yeah, a reasonable fraction. And who's used it in anger? Okay, no one, yeah, okay. And who knows about history matching? Okay, good. So these slides are based on a tutorial I gave a couple of years ago at NIPS, the big machine learning conference, to about 1,000 people. And that was a 2-hour tutorial. Okay. And what I learned from doing that was that I had too many slides, essentially. And my intention was to cut them down. But as I was going through, I thought, oh, my thinking's changed on this. So I kind of cut some out and added some. So I got way too much. Okay, so I kind of covered my favourite bits, but I'm very happy to be interrupted to go over bits slower, or to go back, or to skip ahead and sit down. Okay, and just guide me from the floor if you like, if you want me to go slower in places. Okay, so my laptop's recovering from lunch and going a bit fuzzy when I change slides. So just to set the notation, what I'm interested in are inverse problems. So what do you call it? Calibration, parameter estimation, inference. I call it Bayesian inference. Okay, and the setting is that we've got some parameters that we want to learn about, theta. Okay, and I've got a complex model, a simulator, which I'm going to call f of theta. That's going to be a stochastic simulator, typically. And that's going to generate some output, which I'm going to call x. Okay. I'm going to assume a scientist has come along and given me some observational data d. And I want to go backwards. I want to say what theta values could have led to d according to my simulator f. Yeah, I want to go backwards. So I'm going to approach this in a Bayesian fashion. Okay, so I'm going to try to work out the posterior distribution of my parameter theta given the data d. Okay. And so prior times likelihood type of thing. So when we were talking about putting this program together, there was a discussion amongst the organisers about whether ABC rightly belongs at a UQ conference or not. Okay? Whether it's capital UQ or whether just it's kind of the standard type of UQ that statisticians do all the time. And I guess the history of ABC is arisen out of genetics and computational statistics, and there's not much of an overlap between the capital UQ field here and the ABC community, okay? In part, I think, because of the type of models we look at. Okay? So this is not a model I've particularly worked on, but it's the kind of model I aspire to work on. So I'll just show you and explain why it's somewhat different to some the other models people talked about here. So this is a cellular POTS model of a human colon crypt. Okay? I'll show you a simulation in a minute. It generates some stem cells. Okay? They're going to generate a compartment of amplifying cells, and they produce colon cells. Okay? We want to simulate someone's colon crypt over the period of their lifetime, okay? And then compare the patterns we see in the simulation to data to learn something about an individual. Okay? So if I just show you this, if it works, so it does work. So these red cells are the stem cells, these are the transient amplifying cells, then it's going to produce colon cells, okay? And this is just a Markov chain, a stochastic simulation, okay? And it's simulating through time as the cells in this colon crypt grow, okay? And so that's simulated about 10 days of this individual. Okay? And so to simulate what the pattern might look like in a 50-year-old man who you suspect of having colon cancer, you have to simulate this for about an hour. Okay, and you get a pattern. And then we want to say something about the number of stem cells and so on, some of the parameters. Okay, so this model has unknown parameters, like all the other talks, okay, but it's also stochastic. So many of the talks we've seen, people have had PDEs, and they might call this a stochastic model because they've got random unknown coefficients. Okay? But the type of uncertainty there is kind of epistemic uncertainty. They don't know some field, they don't know the permeability field. Okay? But it's a deterministic simulator. If you tell me the permeability field, okay, the simulator will give you the same thing each time. The PDEs will give the same solution each time. Okay? Here we've got unknown parameters, but the model itself is inherently random. Well, there's random numbers in it, okay, because we believe the situation we're modelling is random. Okay, so these type of models are very popular in genetics and ecology and epidemiology and so on. The other feature of this model is that it's got an unknown likelihood function. Okay, it's very difficult to compute the distribution of that model. If I wanted to work out for a given parameter setting what the distribution of the patterns we expect to see is, it would be very difficult to do that. Okay. It's computationally expensive, so I'll come to that towards the end of the talk, how we can deal with that. And it's also imperfect. Yeah, it's, cell growth in a colon is going to be very difficult, so it's an imperfect model. Okay, so just a basic primer on Bayes for a minute, and why Bayesian inference is difficult. So the Bayesian inference is philosophically simple in some sense, okay? At least compared to frequentist methods. Everything's just probability, and we just use Bayes' theorem for everything. We may disagree about what probability means and all the rest, okay? But in some ways, it's a simpler framework. Okay? Computationally, it's difficult, okay? So that's why we have to resort to these sampling methods like MCMC that people have talked about. So typically the difficulty is, in Bayes' theorem here, that we don't know the denominator here. We don't know this normalizing constant. Okay? We only know the terms of the numerator, and so we can do MCMC to get around that and to generate samples from this posterior distribution. Okay. But some problems are harder than that. They're more difficult. We don't know the denominator. We might not even know the likelihood term. Okay. So there's a kind of a fairly small class of problems that are called doubly intractable, and that's where the likelihood function is only known up to a normalizing constant that depends upon the parameter. Okay. And there are a certain type of likelihood method we can use to solve them. So Ian Murray and Dave Mackay and people, Zubin Garamani, all in Cambridge, did those kind of methods about a decade ago. A harder class still are the kind of problems that I'm interested in, where the likelihood function is completely unknown. Okay, we don't know anything about it at all, okay, but we can simulate from it. Okay. So these are what I'm going to call completely intractable problems. So we can't compute anything about the likelihood function. And of course, saying it's unknown is kind of a subjective thing. It might be unknown to me, but Ralph might be able to calculate it in 5 minutes after lunch, type of thing. But one way or another, right? It's unknown to you in some way. Okay, and this is quite common. That you add a Gaussian to a Poisson and multiply it by gamma. It's going to take you all afternoon, if it's even possible, to work out the law of that random variable you've just created. But I can simulate it from it in in 2 seconds in R. Yeah, and so it's very easy often to simulate from these models that you can't actually do any likelihood calculation for. So it's these kind of completely intractable models where ABC is useful, okay? And they arise all the time in biology, because as soon as you've got a branching process that is unobserved, okay, or a stochastic difference equation, any kind of complexity like that very quickly leads to intractability of this type. Okay, and that's what ABC for. So ABC is kind of one of the few methods we can use to do inference in these cases. So ABC stands for Approximate Bayesian computation, but of course there are lots of approximate Bayesian approaches to computation. Okay, so ABC I prefer as a title. It tends to refer to a particular type of Monte Carlo algorithm that uses simulation. Okay, so I'm going to use ABC more than approximate computation here. Okay. As I say, I've said this already, they don't require explicit knowledge of the likelihood function, and we do all the simulation with all the inference using simulation. And so because of that, because we don't need the likelihood function, they're sometimes called likelihood-free methods. Yeah. That's a poor name as well, because they're not likelihood-free. There is a likelihood function. Yeah, it's just we're only using it implicitly via the simulation. We're just not using it explicitly to do a Metropolis Hastings sample or anything like that. Okay. So ABC, I think it's a nice title for it. Okay, so they're widely used in a variety of different disciplines, mainly kind of computational biology areas. So they kind of arose out of genetics. They become very popular in epidemiology, ecology, sciences where you have stochastic models. Okay. They're increasingly being used in some harder sciences, so like astronomers have noticed them in the past 5 years or so and use them increasingly, and the machine learners have used them extensively in the past 5 years for computer vision type of problems. Okay. Why are they so popular? Well, there's a variety of reasons. First, they're kind of trivial to implement, at least a basic form. Okay. Whereas, I don't know, if you want to do an MCMC algorithm, say the thing Rob was talking about this morning, multi-level MCMC with reversible jump steps, you're going to need a highly qualified individual with a lot of free time on their hands, right? They're difficult to work, whereas you could do something basic and crude, fairly simple, the ABC type things. Okay? They're also kind of fairly intuitive, So if the first ABC paper is kind of either this Tavare one or the Beaumont one or Pritchard, okay? But the longer we've looked, we can find more examples of people doing this kind of thing back in other literatures. So in statistics, Don Rubin and Peter Diggle had done things in the past. But every literature has ABC type ideas for doing some sort of fitting. It's a very natural idea, which I've not told you what it is yet. Okay. And it can usually be applied. You can usually do something that kind of way. So consequently, they're kind of widely used in some disciplines, let's say. Okay, so I thought what I'd do is just tell you the basics, tell you about some of the directions, kind of the main directions of development of the past 10 years or so, and then a few thoughts on the kind of areas that I'm interested in, particularly for the next, for this program. Okay. So, what's the basic idea? What's the basic likelihood-free setting? So you probably all remember from university, if you took any kind of master's level stats courses, rejection sampling. Okay. So remember, the aim here is to generate samples from the posterior distribution, so posterior theta given the data D. So the rejection algorithm, I think it's von Neumann, okay. You pick a value of theta from the prior, okay, and then you accept theta with probability proportional to the likelihood. Okay. So you pick from the prior, toss a coin with this probability of heads, okay, and if it lands heads, you keep theta. If not, you reject it and do it again. Okay. And if you do this, you get IID draws, independent, identically distributed draws, from the posterior. Okay. So this works. Okay. Our problem is we don't know this likelihood function. Yeah, this is unknown, so we can't use this. So there's kind of a mechanical version of this, if you like. It's like a mechanical version of Bayes' theorem. So this says, start by picking a theta from the prior, and now simulate some data from our model. So F is the model that generates samples from this likelihood. Yep. So pick a theta from the prior, simulate from the model with that theta, okay, and now accept theta if the simulation exactly matches the data. Yep. Pick theta, simulate from the model. If the model matches the data, keep your theta, it's a good one, put it to one side, put it in your histogram. If not, just do it again. Okay. And this doesn't have the likelihood in anywhere except implicitly here because we've simulated. Okay. And this is exact. Yeah, this is a mechanical version of Bayes' theorem. This gives us the same thing. Well, what's the problem here? Well, we're never going to get any acceptances, right, for a continuous, high-dimensional data, whatever. It's never going to happen. So this is where we get the A in approximate Bayesian computation, ABC. Okay. We're just going to accept now if we're close to the data. Pick from the prior, simulate from the model. Okay. If the simulation is close to the data, okay, accept. Put it in your histogram. Yep, it's a sample from our approximate posterior. And we're going to measure close here by some distance function I'm going to call rho, and some tolerance epsilon, which says how small the distance has to be. Yeah, we can argue about that later. Okay, so epsilon here kind of reflects some kind of tension between computability and accuracy. Yeah. What happens if epsilon's infinity? Well, if epsilon's infinity, this algorithm says draw theta from the prior, do something, it doesn't matter what, accept it. Yep. Draw from the prior, accept it. Okay. And so we don't learn, we're just going to generate simulations from the prior because we're always going to accept if epsilon is infinity here. Yep. And so if epsilon is infinity, we just get the prior back again. But it's really cheap to compute. Yeah. For every simulation I do from the prior, I get an acceptance. Okay, but I've learnt nothing. If epsilon's 0 and rho's a metric, then we're back to the previous slide. We only accept if there's a match and it's exact. Okay? So if epsilon's 0, we get the posterior. If it's infinity, we get the prior. Okay? This is very cheap. This is prohibitively expensive. Okay? So epsilon kind of controls the accuracy and the computability. Yeah? We can do more computation, get more accuracy, less computation, less accurate. Okay. So just in pictures, what's happening? So I've just created a fake model here. So imagine I've got one parameter that varies between -10 and 10. Okay. So this plots from -3 to 3. So from over here to over here. Okay. And I've made up some models, some simulators, a likelihood function. Okay. And it's just a Gaussian that's quadratic in the mean and cubic in the quadratic in the variance. Okay. And I've imagined we've got a single observation that D is 2. So what ABC says is pick a value on the x-axis somewhere, pick a value of theta from -10 to 10. Do a simulation from x, from here, for that theta, and I've plotted it. I've got theta on the x-axis, the simulation on the y-axis, okay? And I've just drawn a line through d equals 2, that's a solid red line here. Okay? And then I've drawn a ball around it. So I've got this is my distance function. Okay, I've got a ball of radius 10. Okay, and so that's the dashed lines represent the width of the ball, and I've just coloured red all the points that lie in here. Okay, so ABC says pick something on the x-axis, pick a theta, simulate a d. If we're close, keep it. Okay, so what I've got over here is the histogram from all these red points. These are the red dashed line. And the black line here is the true posterior. Okay, if I have to do Bayesian inference properly here, I'd get the black line here. So this is my ABC approximation to the true posterior. Okay. So you can see I've done some learning. I've learnt that the value of theta is not bigger than 3, and it's not less than -3, but I've not really learnt anything in the middle. It's just somewhere in there. Okay. Yes?
Just a question. In your model of the observations, you have noise, or it's just a model that is stochastic?
You could have noise, but the way people typically, I mean, there's a variety of ways of doing it. Typically, people would include it in the simulator, okay? But you could pull it out the simulator. If you've got a complex stochastic simulator and you're adding Gaussian noise, you can deal with the Gaussian noise in a likelihood framework. Yeah, so you don't need to do it. But typically, I guess people were dealing with sequence data, and so the noise was of a different type. So it was just in the simulator. But yes, you could. Yeah. Okay. So let's decrease epsilon a bit. Okay, so if I decrease it down to 5, it was 10 before. Okay, you can see we've started to resolve some of these different modes a bit. Yeah. We've learned a bit more. The approximation is becoming a bit more accurate. Okay, if I reduce it a bit more, so if I reduce it down to epsilon equals 1, you can see we've got a very good approximation now. Yeah. This is what Bayes' theorem is doing, right? If I took an infinitesimally thin slice through here and did the calculation properly, that's just what Bayesian, the posterior distribution is calculating, a thin slice through this surface. Okay. So the accuracy depends upon epsilon, but we have to do more and more computation to draw this histogram. Okay. Oh, one more thing before we kind of get into something slightly more advanced. Normally, of course, this picture's got a one-dimensional parameter and a one-dimension output. Typically in ABC, we're doing it for very high-dimensional outputs. Yep. So think about sequence data from some kind of a genetic experiment. Yep. So you've got millions of outputs. Okay, and we can't do this matching in millions of dimensions. Million dimensional haystacks are hard to find your needle in. Okay, so we have to reduce dimension in some way. So normally what we do, we have a summary statistic S, okay, which just projects to a low dimension. Okay. So typically people do things like look at the mean, the median, the variance, or whatever it is that they think is interesting. If there's different types of outputs, means are different outputs, okay, and try and match them. So you're going to pick from theta from your prior, simulate x from your simulator, and then summarize both. And if the summaries are now close, accept theta. Yeah, Bob.
I guess you'll get to that, but there will be a very subtle interplay between the number of simulations and the epsilon, no? Because the more you have, the finer you can choose.
Yeah.
Think to that, or
okay. And with the dimension of S as well. Okay, the dimension of S is the interesting one to play between the dimension of theta and the dimension of S. There's kind of some nice theory about optimal dimension of S. Okay, and if S is a sufficient statistic in a statistical sense, we're kind of back to the previous case. We've not lost any information by doing this summary. Okay, so this is really simple. Yeah, no matter what your level of statistical training, you can code this, right? You don't need any stats, MCMC expertise or anything like that to do this kind of thing. And so consequently, it's become popular in biology labs. Okay, so what's ABC doing? Well, remember we started out wanting to solve this inverse problem. I could have written an explicit error term in here, but I haven't. Okay, but we wanted to find those values of theta for which f of theta equals a data. Okay, that's what we wanted to solve. It turns out what we're instead solving is that d is f of theta plus an error term, e. Okay, and we can easily show that the error term under the algorithm I've shown you has a uniform distribution on a ball of radius epsilon. Okay, so you wanted to solve this. Instead, you solved the problem where you've added a uniformly distributed error term. Okay, and you're doing kind of exact Monte Carlo exact inference for the wrong model. Okay, so that's what ABC is doing. Okay, and of course we don't like this uniform thing here, so it's easy to generalize this. Yeah, it's easy instead of just accepting or rejecting in this step, we can accept or reject with some probability. Okay, so we can generalize ABC, so we can say pick theta from the prior, simulate x from our simulator, and now accept the pair theta x with this probability, okay, where it's just some arbitrary probability we assign to the relationship between x and d. Okay, so there you could build in your measurement error term if you wanted. Yeah, it could be your Gaussian measurement error or whatever. Okay.
I was just saying, one of the things that seems attractive is quite often we don't know the distribution of the errors.
Yes.
And so what do you assume in that case?
People just assume this uniform error.
That was my guess.
Yep.
Yeah, when in lack of knowledge.
Yep.
Okay.
So if I set this term to be 1 or 0, according to whether this distance is less than epsilon or not, I'm back to the previous algorithm here. So that's what's happening here. And I should say, we can use this if you wanted to model measurement error or discrepancy or all kinds of kind of structure we might know in our models. Okay, but people typically don't. They just have a uniform cutoff here. Okay. Okay. So what are the key challenges then for ABC? Well, there's kind of two aspects, and I'll talk about both. Okay. One is the scoring problem. Okay. We normally score in statistics the quality of a parameter according to the log likelihood function, right? Given a theta, I compute the log likelihood function, and that tells me how good that parameter theta is. That's the score I use in both classical and Bayesian statistics. Yeah? In ABC, we don't have that as an option for a score, so we have to determine a new score. Okay, so I've described one particular score that depends upon a distance function, a summary, and maybe a tolerance, something like that. And they control the theoretical accuracy of the approximation we could achieve. Yeah? But we don't have to use the kind of thing I said here. We can use other kinds of scoring approaches, which I'll briefly talk about. That's one challenge. How do we find good ways of scoring parameter values? The other one is computation. Okay, so computing an approximate posterior is usually difficult. One of the reasons for not using uniform here, actually, is because if you want to do MCMC or any kind of sequential sampling algorithm, okay, having a 0-1 step in your kind of approximate likelihood kills any kind of smoothness you have in the target, and it makes it very difficult to mix. So just having a Gaussian thing here can aid smoothing, for example, aid mixing, for example, in a MCMC scheme. Okay. Okay. So, as I say, the first kind of time this was noticed in statistics was about 2003. Mark Beaumont, David Balding and colleagues published something more statistical. Okay? And then Rob mentioned the SMC mafia earlier. So all the kind of very intelligent French Monte Carlo crowd got hold of ABC, and for a few years every type of Monte Carlo algorithm you can imagine was turned into an ABC version, okay, and studied. Okay. So I'll just show you one example of how we turn an Monte Carlo algorithm into, yes?
To come back to my question, I'm not sure, maybe I didn't understand your answer. So you seem to pick an epsilon and then you analyze your error.
So I understand what you mean, yeah, go on.
I would choose the epsilon depending on how many samples I have.
Yes, so typically that's what people do, you're right. Okay, so typically people say, oh, I've got a budget of 1 million simulations, I'll take my best 1,000.
Yeah,
okay, so, sorry, I misunderstood what you're saying, yeah. Mm-hmm. That is typically what people do, okay? I think it's more justified, potentially, to think carefully about what the right tolerance is. And that's what Michael would kind of recommend we do in a history matching type of setting. Okay? But the norm is to just take a proportion of whatever you can afford. Okay, so the version, the algorithm I've shown you so far is the rejection ABC. We just keep sampling repeatedly from the prior. Okay, that's very inefficient. If you've got a 10-dimensional parameter, prior space can be big compared to posterior space, if you like, and so it's inefficient to keep sampling from the prior. And so we want to use things like MCMC or SMC or EP or multi-level Monte Carlo. There's an ABC version of that now. Okay. Ral Tamponi, I think, did it. Yeah. Unsurprisingly. Okay, so how would we do it for MCMC? What's the difficulty with doing this? Okay, so the distribution we're targeting, okay, so is this ABC approximation. Okay, So this, I've written this in terms of a distribution over theta and x here. So x is the simulator output, these are data, theta is the parameter. I've written it in terms of doing it in the joint space, so I don't have to marginalize out. It just makes the presentation slightly easier. Okay. So this target is the prior times the likelihood function, which we don't know, times the ABC acceptance kernel. That's the kind of thing we're targeting here. Okay. So we've got to, if we want to do MCMC, Markov chain Monte Carlo, we have to describe a way of simulating a Markov chain such that the samples converge to being samples from this. Okay. So what's difficult in this? If we write down the Metropolis-Hastings acceptance ratio, okay, so if Q is just our general proposal to moving from a pair theta x to a pair theta prime x prime, okay, when we substitute in the target likelihood, we're going to get the target distribution. We're going to get the likelihood term in that we don't know. Okay, we don't know this term, and we need it to cancel. So the consequence of this is the type of proposals we're restricted to are of this form. Okay, so we want to move in theta x space. We can choose anything we like for the move in theta, but when it comes to a move in an x space, we need to have a likelihood component here so that it cancels out down here. Okay. And so this is, if you know about MCMT, this is not going to be a nice type of move. Okay? This is an independent sampler in X, essentially. It says, move theta, well, at your new theta, just simulate again from the model. Okay? So one, this is inefficient. We keep having to sample from the simulator. Okay? Two, it restricts our choice here. We have no choice about this, give or take a bit. Okay? Three, it can make mixing really difficult here. Okay? If you happen to hit upon a good X by mistake, okay. So you're at theta, okay, it's a very stochastic simulator, you just happen to get lucky, you get a really good x, okay. You move to a new theta, it might be a better theta, but you might not simulate as good an x again, and so you get stuck in space, okay. And so consequently, these algorithms are really difficult to make work well, because they mix very poorly. Okay. But we can do these type of things, they do improve upon rejection sampling, but they're not easy to necessarily make work well, particularly MCMC is particularly prone to problems. Okay, so mostly what people do are sequential Monte Carlo algorithm versions of it, but they're slightly harder to write down, and Peter did such a good talk on Tuesday talking about them. I thought I'd do MCMC instead. Okay, but any type of Monte Carlo algorithm you can think of, someone has probably done an ABC version of it at some point. Okay, you just kind of add this to your target some way. Okay. The other key idea, the ABC practitioners tend to fall into two camps, either the ones who try and do efficient sampling, they're kind of the more statistical end, and those who try and do regression adjustment. Okay. And with the idea behind regression adjustment is to try and re-weight your samples according to how good they were afterwards. Okay. So we've got the summary of our simulator output, I've slightly changed notation here, I apologise, to S, okay, and the summary of the data, which is SOBS. Okay. And there's two kind of key ideas. This goes back to Beaumont. Is to use a non-parametric kernel density estimate to emphasise kind of the best values here, and then to kind of use a model for the conditional expectation to try and adjust these parameters in some way. Okay. And I'll show you pictures to make this clearer. Okay. But I say this is kind of a separate approach to doing things because you can't do this in a sequential way. So you can't do this with MCMC or SMC or anything more efficient. And so people tend to do one or the other. They do this or they do MCMC or something like that. Okay. So what's happening in pictures? So this is the same diagram as before, but I've switched the axes around to emphasize the modeling direction. Okay. So I've still got, the points are still draws from theta and the simulator. Okay. But now I've got theta on the y-axis and S on the x-axis, the observation on the x-axis, and this is my one observation. Okay. So what they do in the regression adjustment is they plot all these points, okay, draw a line from the data, and then they fit a model in the neighbourhood of the data, okay, and then they're going to shrink all these points down onto where the data are. Okay, so they look at the residual. So this is my green line is my model, my simulator, my statistical model. I fit to this curve of points. Okay. And it tells me there's this kind of slope. You look at the residual of your points and then try and shrink it down onto where the posterior is, okay? To where the data are, okay? In the hope that you get an improvement in accuracy. And at the same time it's doing this, you're going to weight the points more or less depending on how close they were. So these points here will get a lower weight from these points here. Okay, so it's kind of a very crude sounding idea, but it just seems to work very well. Okay, so just to show you an example of it working. Okay? The truth here, it doesn't matter what the model is, was the black curve. Okay, the red points, we're just doing it from rejection. I just generated 200 points and did it with rejection sampling. And I just applied that very simple linear regression adjustment. It's just literally linear regression, and I get the dashed line. Okay? And it seems to work even better in higher dimensions compared to other approaches. Okay? So in high dimensions, it seems to carry on working reasonably well because you've summarized everything in a way that you haven't when you're doing the efficient sampling approaches. Okay. Okay. And of course, anything people do with linear models, people now do with neural networks or any other kind of machine learning type of model. Okay. And there are very nice implementations of this actually. There are no nice implementations that allow you to do MCMC or SMC in these settings because they're hard to make work. Okay? But if you want to do these kind of regression adjustment things, it's a simple R package and you just feed it your prior and your simulator and it does the work for you essentially. Okay. Okay. So one of the two challenges I mentioned was the use of scoring. Okay, how do we score our runs? And part of that is how do we summarize the simulator output. Okay. So we said we're going to project the data D down to a lower dimensional summary. Okay. And we need to think about good choices for this projection S. Yeah. If you know something, that's great. Yeah. If you have experts who can tell you things, that's good. But how can we find good choices of S that make this a good approximation here? Okay? That don't lose us too much information. So before I tell you what people do, I just want to just kind of give a warning here, really, that there's lots of automated methods for doing this. Okay, for finding good summaries automatically. Okay? But I think you need to be wary of them quite often, okay? Particularly if you're in a misspecified situation. Okay? Typically how they work, they say, well, what summary here is particularly informative about theta? Well, they don't mean informative, they mean restrictive. Which summaries particularly cause my prior to change the most? Okay? So you look at the posteriors from different choices of the summaries and try and find the summaries that cause the prior to change in the largest way. Okay? And that's fine if you're not in a misspecified situation, but as soon as you're in a misspecified situation, so your model's incorrect in some way, it can be very difficult, well, it can be very misleading. Yeah? You can find that some summaries may well be restrictive, but are not necessarily informative about the parameter in a meaningful way. Yeah? So if you've got expert judgment, it's typically much better to go with that instead, okay? In my opinion, in many cases. If you've got an expert who strongly believes that this simulator is good for predicting this kind of aspect of the output, that's great. Okay. So the kind of example I have in mind, right, is if you had a dynamical system, yeah, and your dynamical system wasn't designed to predict phase information, but it could produce things like periods. Okay. If you use summaries to fit your simulator that weren't phase invariant, you're going to learn potentially a lot about theta, but not learn anything meaningful. You're just going to mislead yourself by using these non-phase invariant summaries, even though the summary wasn't designed, the simulator wasn't designed in that sense. Okay. So there are two aspects to the ABC approximation. Okay. There's the error that we accrue when we summarize. Okay. So when we use the summary instead of the full data, we get an approximation here. Yep. The other approximation is from using this ABC kernel, from saying accept if we're close only. Okay, if we're not close, don't accept. Yep. So two sources of error, one that accrues from summarization, one that accrues from the ABC step. And they trade off against each other here. Okay. If we think about this, if the dimension of S is small, okay, we've got a large compression of the data. Yeah? We've taken our high dimensional output D, we've compressed it down a long way, Yep. And so we've lost a lot of information here. Okay? So this approximation is poor, but when we come to search for close matches in this lower dimensional space, search is easier in lower dimensional space, essentially, and so it's easier to get a close match here, and so this error will be smaller. Okay? Conversely, if the dimension of S is large, if we don't project down too much here, if we don't compress too much, okay, this error is going to be small, because we've not thrown away too much information, but doing a search in a higher dimensional space is harder, again. Yep. Think your d-dimensional haystack. Yep. Trying to find a needle in the higher dimensional spaces is harder. Yep. So the trade-off between these two things, okay. And so the work done by Paul Fernhead and Dennis Prangle in 2012, an important paper, showed us that it is optimal in some sense here to choose the dimension of your summary to be equal to the dimension of the parameter. Okay, that's optimal in a fairly restrictive sense of minimizing the mean squared error of your point estimator, but it's the only bit of theory we have to guide us in how much compression we should do. Okay? And so that's kind of the rule of thumb people try to aim for here. Choose a summary that matches in dimension your parameter dimension. Okay. I mentioned that machine learning people have done a lot of work recently in this area. Okay. And one of the main areas they've done this is that machines are much better, of course, at classification than humans, and so at scoring, they've developed lots of interesting ways to avoid this way of having to do summaries and distances between summaries. Okay. So the game now is more about classification of things. So probably the first people, they're not really machine learners, they're statisticians, Jean-Michel Marin and colleagues. Okay. They were using random forests here to do this. So their idea was to create a large library of simulator runs. So they generated thetas and x's from a prior and simulator, did a large value. Okay. And then they trained some sort of machine learning regression model to predict the parameter from the output D. Okay. So to predict theta from x, so the opposite way around to what we want, and then use that as your summary. Okay. So then you're going to accept theta if your prediction at the simulator output x equals the prediction at the data. Okay. So it takes you a while to get your head around this, but it works out to empirically work very well, particularly in these high dimensional problems where it's very hard for humans to look at 1,000 dimensional output and think what's a good summary here, but a random forest trained on 10 million evaluations works quite well. Okay? And people have done it with images, so convolutional neural nets and things like this, and these kind of methods are very good at extracting the right type of information for doing these things. Okay. And then if you move in machine learning circles a bit, there's a lot of interest at the moment in these generative adversarial networks, which a speaker mentioned the other day. And the idea there is that you play a game between the generator and a classifier. Okay? The generator is your simulator that spits out samples. Yeah? Your classifier tries to classify between whether it's from a simulator or from the real data or not. And they play a game against each other. They're adversaries in the game. The generator generates data. The classifier tries to tell it apart from the real data. Okay? And you train them both simultaneously. Okay? And this is proving phenomenally successful in machine learning at the moment for a variety of regions that I don't think have really understood, but they're just throwing huge amounts of CPU cycles at these things, and it seems to work well in high dimensions for discriminating between these things. Okay, and there's other work as well. I think the key thing about all of these is to stress the point again, is that they seem to work really well in simulation studies where you know you're not misspecified, where the truth lies in the set of candidate models you're considering. Okay? Misspecified situations, anything can happen because you're just learning patterns. Okay? So it's problematic, potentially. Okay. Any questions so far? Gary?
As a cardiac modeler, what's the difference between ABC and history matching? Is
Good
ABC
question.
kind of history matching with a prior or something?
I will tell you right now, okay? It wasn't planted, actually. Let me skip ahead. Okay. I'll come back to that in a minute. I told you I had way too many slides. Okay. So, we can think about doing inference for misspecified models. So that the picture to have in your head, I think, is you've got some set of models, okay, so these are all parametric models, so they've got some theta that describes them, okay, and we've got a true generating model that lies outside this set, okay. So we're trying to do inference in here, okay, and we're trying to find the best model in here, but the true model lies outside of here, okay. It's not in our family of models. What can we do? So there's a very nice paper that's been mentioned several times by Mark Kennedy and Tanya Hagen from 2001, which basically expand this set of models here by bolting on a kind of a non-parametric Gaussian process term. Okay? So they expand from this small parametric framework to a big non-parametric infinite dimensional space. So the way it's described in Kennedy and Hagen is you just bolt on a Gaussian process. You add on a flexible non-parametric regression term. Okay. Although that idea is kind of really nice and has been very influential, in practice we've found that most people have found it doesn't work very well. Okay. Except in a number of restrictive situations where you have the right kind of repeats. Okay. So this is a paper, an example from another of Tony's papers showing it doesn't work very well. Okay. So they say that let's imagine you've got a simulator that, you've got reality that's generating data from this model, okay, and you've got a simulator that's an imperfect version of that. So it's the same as reality, but you're just missing the denominator here. Okay. So the first thing they point out is that if you ignore model discrepancy here and just fit the simulated data, you get a really confident and wrong answer about what the true what the parameter value is. You do inference for theta, you learn theta is 0.5 something, okay, and the true value is 0.6 something. You're confident and wrong. They then say, well, let's do inference with the simulator, but bolt on a Gaussian process. Yeah, add on a Gaussian process discrepancy, and it improves it slightly, but we're still wrong. Okay, so you're less confident now. You've got a discrepancy term in your inference, but you're still getting the wrong answer. The true parameter value still lies largely outside your posterior. Okay, and this is something we see all the time in practice. So what's happening here? Well, there's two things that's happening. One, it could be that the data generating process still lies outside of this expanded set. Yeah? You've expanded the class of models into this infinite dimensional thing, but it's not big enough. Okay? More likely, it's a lack of identifiability, that you're just converging in the wrong place. Okay? So this is kind of a rewrite of a statement in a Gelman, Betancourt and Simpson paper appeared a few weeks ago. It says a GP is an incredibly complex infinite dimensional model which is not necessarily identified even asymptotically. And so the posterior can concentrate not on a point but on some submanifold of parameter space, okay? And the projection of the parameter space continues to impact the posterior as more and more data are collected. So in other words, we never really forget the prior in these situations. You've got this complex, huge, infinite dimensional prior that we don't fully understand, okay? And the posterior calculation converges to some submanifold of this, and which bit of it we land on is kind of by chance, okay? And that's what's happening here, I think. Okay, and so the solution in this Brunion-Zotto and Hagen paper is to try and model your way out of trouble with more prior information, okay? Which is great if you've got it. If you know more, put it in, okay? So back to ABC and history matching, and to Gary's question, I think. I think ABC was proposed as a method of last resort, if you like. It's what you should do if you have no other choice. Yeah, if you don't have a likelihood function, you're stuck. What can we do? Well, ABC is something. Okay, this is something. Yeah, let's do it. But anecdotally, at least, there's evidence that it works particularly well for misspecified models. Okay. So why might that be? Well, there's a method called history matching, which people have mentioned here. Michael mentioned it in his talk, and other people have mentioned it. Okay. So history matching was explicitly designed, I think, for inference in misspecified models. Right? Okay. And it turned out to be very similar to ABC. Maybe not as how I've written it here, but what's happening in history matching is we define some score. Okay, so the score maps our distribution is a function of our distribution, our data, okay? And given any observation, y, okay, it scores that particular model. Okay? And this is the choice that's always used in history matching. What they then try to do is find what they call a not ruled out yet set, which I'm just going to call a plausible set, which Michael hates. Okay? But they say that theta is plausible if the score isn't too big. Okay? So this thing measures the distance from the data to the mean and it kind of scales it by the variance. Yeah? So it's a sensible kind of score. And say if this isn't too big, theta is probably not too bad, let's keep it. Okay? So it's designed as a conservative method. Okay? And it's designed to work in situations where you have misspecification, the idea being that you don't get the kind of concentration, posterior concentration that you get with likelihood-based methods. Okay? And you don't falsely rule things out by mistake. So how is this similar to ABC? So ABC uses this approximation, okay, and I've written it differently every time I've written it down. Okay? But the ABC approximation is essentially the prior times by the expectation of an indicator function of whether some score is less than some tolerance epsilon. Okay? So ABC also uses a score. It scores as your simulator output or some estimate of the distribution of your simulator and the data y, okay, and says except if that score is good enough, if it's less than epsilon. Okay? And what you're implicitly doing is averaging over that, yeah, when that's what you're doing in the Monte Carlo. Okay? So ABC is approximating this kind of thing. So if, Gary, your prior is uniform everywhere, yeah, if your simulator is deterministic, and if I use the score here, that's this one, then we're targeting the same thing in ABC and history matching. They're not designed in that way, okay? And in history matching, they put lots of thought into all these things. In ABC, as I said to Rob, we tend to just pick the best value we can get away with, yeah? But they're kind of algorithmically, they're targeting the same thing, okay? Okay. So why is it then that these might work better, anecdotally, why is it that they might work better in misspecified situations than likelihood-based things? Yeah? Is that even feasible? Okay. So this is the main thing I want to explore over the time while I'm a program participant here. Okay. So if anyone's interested in talking to me about this, that'd be great. So I have kind of three thoughts, if you like. The first two aren't really very controversial, I think. But they differ from kind of a full likelihood-based analysis. And firstly, they only use some aspect of the simulator output. Yeah? So they typically hand-pick summaries. Yeah, in ABC, we pick our summary statistic, and that gives you a great amount of power in saying, well, the simulator's good at this, not so good at this. I'm going to downweight this aspect of the output. I'm going to put great emphasis on this aspect of the output. And history matching does exactly that. Potentially, they use generalized scores or loss functions. Okay. So in history matching, they use this score, okay? But there are other scores we might choose to use. So Phil David has studied classes of proper scoring rules that are robust to certain types of misspecification, to outliers in particular, okay? And so perhaps it comes about from the scoring. The log likelihood is known to be highly sensitive to misspecification, right? So we use log likelihood in Bayesian frequentist statistics generally, yeah? And they're known to be sensitive to misspecification. But finally, I think this thresholding makes them somewhat conservative. Okay? So both Bayes and maximum likelihood kind of tend to have the property that they concentrate asymptotically. So in maximum likelihood inference, what happens is we get more and more information. We converge to this point here, okay, which is the model in this set that minimizes the KL divergence between G and my model class. Okay, and Bayes does the same. Yeah, you forget the prior, and von Mises the same. You converge to the same point under some conditions. Okay. And posterior concentration makes no sense to me if you're in a misspecified situation. If the link from your parameter theta to your data d is a model that you know to be wrong, it makes no sense that you converge to a point estimate as you get more and more information. And these thresholding type things, where in history matching, you start by saying the error is about this big, or in ABC, you say it's about this big, epsilon or whatever, okay? And you can't learn more than that. It kind of sets a limit for the amount of learning you can do. And I think that is potentially what makes them useful in these types of situations. Anyway, these are my kind of 3 hypotheses about what's happening, and I'm interested in exploring whether they're all useful or whether it's just one of them. Yeah, Rolf.
Can I kind of follow up on this? So one of the things, and I showed a really quick example on this, is if you have the statistical model wrong, and hence the likelihood wrong, you're going to get your prediction intervals wrong. Will this do a better job of giving prediction intervals, et cetera, that you can trust a little bit more fully because of the way it's working? Do you have a feeling about that?
It possibly will do, yeah, because you've still got the physics in there from your simulator, yeah.
Not the physics, you just aren't...
And you've not restricted, yeah, I mean, whether it's enough to fix it is a different question, but what I didn't say about the Kennedy and Hagen approach is that will fix your prediction, potentially.
Right.
Okay, it won't fix your inference for theta, but it can potentially fix your prediction.
And what we're worried about is when you start to extrapolate out of data predictions, and that's where...
Yeah, that's where I dislike, everyone dislikes the Gaussian process bolt-on thing. The approach of ABC or history matching in this sense is just to say the error is about this big, yay big, okay? And it's nothing more than that. It's just an error term. There's no learning of it when you're extrapolating.
Right, okay.
It's just the physics plus yay big.
Yeah, I'll talk offline with you about that. I'd love to add to your list.
Okay, thank you. Okay, that's it really. I just want to conclude then. So, ABC allows inference in all kinds of models, yep, for which it would otherwise kind of be impossible. If you're stuck, you can always do something in some way with ABC. Okay. As I say, people generally advise is to avoid it where possible, unless perhaps you're misspecified. Perhaps it does, like history matching. So Michael's advice, for example, would always be to do history matching if there's any risk of specification first, and then do a kind of likelihood-based calculation at the end. So there may be advantages, but generally you want to avoid ABC if you can, because it's a daft way of doing things if you have a likelihood function. And then otherwise there's fancy algorithms for speeding things up and post hoc regression and so on, and lots of interest from machine learning in the past decade really has come in. So thank you.
Richard, thank you for a really, really nice presentation. I think as evidenced by the fact you kept getting questions interrupting you. So that was by your own wish and we took you to it. Are there other questions? Yeah.
So you're simulating from the likelihood,
Mm-hmm.
but that simulation could be wrong.
Yeah.
So should you be learning the likelihood and correcting the likelihood as when you see what you, in some sense? I mean, it could be the likelihood is wrong rather than the...
So you mean fit?
Plumb wrong. I mean, it could be just a plumb wrong likelihood for the physical model. Is there any way of...
Yeah, so you could go down the Kennedy and Hagen route, right, and
Yes.
add another model on top to try and fix things and try and do inference for everything at the same time. Is that what you mean?
So then you would simulate, you would correct the likelihood and simulate from the corrected likelihood rather than the... See what I mean? It's slightly... I only just thought of it, actually.
Yeah, I'm not sure it'd help for inference, though, necessarily.
So, Henry, that's a little bit along the same vein of what I just asked on, because with the wrong statistical model, you're close on it, but not quite. And therefore, you're close on when you do extrapolatory predictions, but not quite. And that was, I think we all are kind of asking the same thing and have the same goals on when you've got some model discrepancy, can this help you? And my guess is it may be very problem dependent, which is always one of the things about model discrepancy.
I don't know. In truth, the work that people have done trying to model discrepancy has all been done largely in a deterministic setting. Okay? When your model is already highly stochastic, and you've got things like the Gaussians and Bernoulli random variables all over the place in your model, it's very hard to think about what a discrepancy is and how to begin modeling it. And so,
and where do you put it?
So I really think it's a difficult, if not flawed, concept to think about modeling it in these stochastic settings. But someone will come up with something, I'm sure.
Other questions? Yeah.
So one of the fundamental factual differences to me between ABC and history matching, whether it's fundamentally factual or just what people actually do, is ABC, you start and you go, you keep on sampling from the whole structure.
Mhm.
Yeah. Whereas one of the whole points of history matching is you start by looking at, like, you choose the easy bits.
Yeah.
And so the bits that you can, because obviously sitting in a complicated model, you're going to have to stick an emulator in there, and some things you can emulate well, some things you can't. So you start by picking off the easy parts. You cut out parameter space. Things that were hard before now become easy.
Yeah.
And it's much more of a kind of a hands-on, gradually improving. So in the end, you only do the careful emulation and modeling in the area where you really need to.
Yes.
And so I wonder about what the ABC version of that is.
Funnily enough, there's what I didn't talk about was using surrogate models in ABC. Okay, and so essentially there's a whole list of people doing these surrogate type of models, which I know is a key part of history matching. And the way I think we should do that is basically copying the history matching approach of. So the idea here is to try and build some sort of surrogate to the likelihood function. Okay, and I think a sensible way of doing that, because the likelihood varies over so many orders of magnitude, is, as Michael says, to cut out easy bits of space first. Okay, build a more refined model in a smaller bit of space, rule out more space, build a more refined model, and so on. So I completely agree with you. Yeah, I completely agree. And I have looked at it.
I'm taking notes, so please, other questions?
There's just an advertisement. There's something called ABCD.
Yes, I've seen that. You're a co-author, aren't you?
ABC, an irresistible acronym, but using it in design.
That's your work.
Others.
And others, yeah. No, I did see it. And I think the nice thing about this surrogate approach is that you can then, it does open you up to using design more carefully, because you're designing for a surrogate now. And so I think just using quasi-Monte Carlo in here helps, for example. So I'm sure you can do something more advanced still. And in fact, what I didn't say, the work I've been doing with James Hensman is on acquisition rules here. I didn't say it because David's talk did such a good job of covering it. But we particularly like these entropic acquisition rules. Okay. So we did what we thought was really interesting work, and then discovered David and his colleagues had already done it, just in a different setting. But it's computation expensive, but you can make good savings by thinking very carefully about where next to run your simulator. It's just that most stochastic simulators are cheap, and so it kind of the overhead of doing it kills you anyway.
Going just another quick, going on from David's talk, which is excellent. It does give the opportunity to do experimental design in very large and very non-standard.
Yes.
So that's a big advantage.
Right. Yes. Thank you.
Yeah.
I work with complex simulators in ecology, and all our models are usually misspecified. All our models are bad, effectively. In my experience, trying to improve our models is actually quite nice. That the likelihood is so sensitive to the fact that models misspecified, and it end up at that little point that you indicated in your inner ring there, because it highlights how our model is actually wrong. So in terms of a strategy for model improvement, I think there's actually something to be said for ending up at that specific point.
That's possibly because you're a sophisticated user. In the sense you've noticed that you've converged on this value and you've got a peaked posterior on the edge of your space in some sense, but often people don't notice that. But yeah, I agree that if you're looking for that kind of information, if you assess model fit, that's very valuable then.
And that is because we are in a program of continuous model improvement.
Right, yes. Yeah.
All right, yeah, one last question, then I think we're going to open up for the general, so please.
In terms of the capturing model discrepancy, this seems to me a bit like it's only going to do the kind of we got the parameters a bit wrong kind of discrepancy. So isn't it the same as Michael's internal discrepancy he was talking about? It wouldn't capture your external discrepancy.
Pass.
So what was the question?
Can you repeat the question?
Is the kind of model discrepancy you might capture by having a big distance around an ABC the same as your internal discrepancy you were talking about?
It could be, depending on how, but if you're doing it really carefully, then it depends how much effort and science go into it. Yeah, I mean, if you're prepared to put a lot of effort and science in, yeah, they're the same.
Does taking the best 1% of your simulations count as science?
No. Understanding what processes you're missing
Okay.
counts as
In
science.
that case, no, we're not doing it.
All right, well, that might be a good place to thank not only Richard, but all of our speakers today.